Great that you're all here. This week, I'm excited to have Matteo Capucci here. Matteo did his PhD in Glasgow in the mathematically structured programming group there, and now works for the Advanced Research and Innovation Agency, I believe that it stands for ARIA, UK. And I've been following his work for a while because he and his colleagues have been doing kind of crazy thing. They've been decided to start applying category theory. And what's exciting about it is that led them to think about complex systems in sort of a compositional way. Try to properly understand what happens when systems are open and can be composed in different ways. And they've come up with a really very nice way to think about this. They use the word cybernetics again, which I'm all for. We should reclaim this word. And today, I think what you'll be talking about sort of fits in the larger picture of trying to understand a modern view of open cybernetics.
Yeah.
So,
thank you, Abel, and thank you for being here. It's a real pleasure to be speaking at the Deep Seminar. What Abel said is true. We used to say that we do categorical cybernetics. I still do categorical cybernetics, I think. This is something I've done not with the Glasgow group, but with Manuel Baltieri, Martin Beal, and Nathaniel Virgo in the past couple of years. So we're trying to understand a bit, like from a more modern point of view, what's going on with the code regulator theorems and with internal model principle. So today I'm going to give you like a very straightforward account of what we think is going on in the classical literature from, let's say, a categorical point of view. And if there's time, also see like the Bayesian interpretation that comes out of that. Of course, it never works the first time. So this is, maybe you all know this, like the original good regulator theorem from Conan and Ashby in their infamous paper, every good regulator of a system must be a model of the system. Like the ideas are really good there, but the math is not. And you can see it from like the statement that it's a bit all over the place. I mean, to be fair, it's like from page 10 in the paper. So of course, there's like a lot of stuff that seems a bit out of the blue, but still, if you read the rest of the paper, it doesn't make too much sense. But it is sort of like sensible, right? That if you have a system that's like governing another system, it's really unlikely that it's doing so without having some idea of how the other system is working. And so that's a compelling idea that's been developed further. I think the best works in this sense were done by Wonham in the 70s and other people related to Wonham. So this is from the paper, The Internal Model Principle of Control Theory, which does exactly what it says on the 10. And this is how they phrase the internal model principle, which is a bit more to the point. So they have this situation in which they have like a classical control theoretic setup. You have a plant, you have a controller, you have an environment that is sending signals or disturbances to the plant, and the controller must keep the plant into some good state, right? And then what they say here is that this is only possible if there is a feedback that reduplicates the dynamic structure of the exogenous signals. So they want to say the controller has some model in terms of a endogenous model of what happens outside. But their notion of model is a bit weird. So this paper is very, very technical, and a model for them, well, again, this like, of course, there's notation that I didn't introduce here, but they have this map, and they say it has an internal model if they have this algebraic condition, which makes sense. Like if you read the paper, it does make sense, but not exactly, I think, like evident, like why this would be a good notion of internal model and why this corresponds to what us intuitively would call internal model, or at least what I would call internal model, which is something more explicit, right? Something like a dynamical system that it's tracking the evolution of the external system that we're trying to regulate in such a way that we can query this model in order to understand what's happening outside, right? Yeah.
You're standing a bit in front of them.
Oh.
Maybe you could
Yeah, maybe let's deactivate this fancy thing.
Yeah, but also I think your physical version.
Oh, my physical
So
self,
let's move the table a bit to the side.
as always.
Both versions.
How is this?
You can move this. Turn it around.
This better?
Yes. I mean, it only for those people further. Yeah, so
I mean, I can move further still.
how do we usually do it? Why is this
I think you
different?
can move it over to this side.
We move it to the other side? Okay, wait. Okay. So I do the table, you do the chair?
Sure.
Oh, I can't see now.
Everybody join the Zoom call. That's the only way we can do this. Yeah, I hope I'm not too in front of the slides, then whatever. I think it's small enough. Okay. Are we good?
Great.
Can I ask one question? Oliver?
Sure.
So I'm guessing the kind of models that they're talking about here are things where the system also doesn't use the model. So there's this kind of decoupling, right? So I'm thinking like, for example, an economic system, you have like a model, like Scholes equation, which is affecting the behavior of the system.
Right.
Is that invalidating with these assumptions?
So actually what they claim is that you must be using the model, right? It's not enough to just have a model sitting there, right? You are like your regulating dynamics is explicitly involving querying the model, right?
Okay.
So it's the other way around. So what they don't account for is the system modeling itself, like the controller modeling itself, right? So in an economic system, you will have like controllers. So it's not like a controller which is controlling an external plant.
No, exactly. That's what I mean.
Yeah, it's like a full regulation problem in which the system itself is part of the regulation
Yes.
problem, right?
Okay.
Yeah.
So this is not including those.
Yeah, and that's actually a good point. So this is within like larger work I'm doing with Nathaniel, Martin, and Manuel, and in that larger work, we try to classify the different regulation problems because there's more than one actually. It's not trivial at that point. Yeah. So where the regulation goal is in the system, right? That lends that yields different regulation theorems, right? Good regulator theorems. Okay, so good. So can we do better than this to some extent? Yes, and Wonham himself, I say Wonham, it's like, again, a bunch of people, but we've been following Wonham because nice work. But they proposed in later work some more, let's say, intuitive versions of this model condition. So there's this paper, for example, that we follow closely. I'll follow closely in the talk, where they talk about regulation in differential systems. And they formulate this notion of internal model, which is basically the existence of a certain diffeomorphism delta between XE, which is the state space of the environment, which is generating like this disturbance signals, and this X minus C, which is instead the state space of, sorry, this should be X plus, right? Yeah, X plus is the state space of the controller in a certain sense that we'll see later. Okay, so this is already something a bit more intuitive, and I'll explain why. At least it involves a direct relationship between the state space of the environment and the state space of the controller, so that we can try to interpret like how like the environment is encoded in the controller, right? But there's some things that they're not really convincing here. For example, they call this endomorph, right? And they assume there is an endomorph. which sort of defies the whole point, right? Because they're trying to prove that there is a map like this, and they assume something which is extremely close to a map like that. And so that's where we started working with Manuel. Is like, can we drop this assumption somehow? And I can say we did. So yeah.
Demanding that it's a different model, and on top of it, demand that it's a good model. Right. Could you?
Well, I could explain to you how Bonham does it, or I can just show you
Okay.
the better version. But yeah, like they first assume it's a good regulator, and then they prove it as a model, right? But in proving it as a model, they sort of like assume there is this diffeomorphism they call the endomorph, which is a bit disappointing in my opinion. So today I'll present our version of the internal model principle, which has some, like, I think, good properties, like being already like hinting at a categorical generalization or categorical like formulation, which should lend itself to also be used to understand compositionality for these problems, right? When you have different regulation problems and situation, like at the same time they're interacting, and that's something very interesting to consider. And then I think our main contribution was like confusing the whole thing. So present like clear assumptions about how the systems work, how they're connected, and exactly what is it that we need and why to prove this kind of theorems. Hello. And then I'll talk extensively about our abstract notional model, which is similar to One-Ham's, but it's more abstract indeed. And then if time permits, I'll tell you about how this is actually all Bayesian filtering in disguise. And surely, like, this is a bit preliminary in a sense. Like, there's a preprint out, but there's way more work to do. And cyberneticists have done excellent work in the 70s and more recently too. So I'm not claiming to have solved like the internal model principle. Like, of course, this is not something you can do in one sitting. So let's start from defining what are the systems that we'll be talking about. So to me today, a system is going to be a fully observable, discrete time, deterministic Moore automaton. And precisely this means that a system is comprised of a set of states, X, set of inputs, I, or observations, you could say, because we use I to observe what happens outside. And then there's a dynamics on X, which is defined by this function. And that's it. So the idea here is that X, which is the state space, is also we could say the outputs that we can get from the system, okay? So it's fully observable in the sense that at any point, any other system could observe what's happening in X, right? So this is an assumption that we make to make everything easier to look at, but it shouldn't be like load bearing. Yeah.
I'm just trying to think about, classic control theory and these things that I understand or know. And then you always have some sort of, this X always has its own internal dynamics. Here we're only looking at observations, or there is any kind of dynamics on X itself. I mean, typically think of the classic idea of something like control, you have your damped spring, then you want spring is going up and down, and then you want to control in such a way that it stops vibrating or whatever. You have this internal dynamics aiming up to observations. Here you only have observations, or am I just completely not understanding what you're
So this is just like abstract definition of system. I'll tell you how we model like the actual situation later.
I think so. If you would, to this update function, give sort of the empty input, you would describing the evolution of X by itself.
Yeah. So if a system,
okay,
if a system has no inputs, right? Trivial interface or autonomous, as we call it later, that's just a dynamical system that evolves by itself, right?
Okay, so just in the update function is also the internal dynamic on X is part of the updates. Which-
But so in this notion of system, also maybe I should have said this, like as a applied category theorist, to me everything is open. Like and so all the systems are like by definition open to some extent. And then closed systems are a particular case of open systems in which their interface doesn't actually participate in the dynamic, right? So if you have like here, X could be ignoring I, right? That's something you could do. And then you have a system that autonomously evolves. Or otherwise, everything that happens at the interface, it's going to affect the dynamic in to some extent, right? Yeah.
You have a related question that maybe is just semantics. Like you say the system is fully observable, and then you say, well, I is an observation, but it's also an input, and all of that confuses me quite a bit.
Yeah, that's a good point. This plagues this field because my inputs are also the observations that I made, you know? Like it really depends on the point of view you take, but I usually read I as the interface and that's it, right?
I is an input or observation.
So it's an input to me, and it also the observations that I make of you, right? So from my point of view, I is the stuff I observe of the world. From your point of view, I is the stuff you give to me, right? And you observe my X.
But you're the system and then the user.
Yeah, I'm the system in this metaphor.
What does it mean to be fully observable?
So what it means is that implicitly, we also have like an observation map here that's like giving outputs so that other systems can use to observe what's happening to me, right? So those are variables they expose or like observables they expose. So in general, you could say you have X and then I have another set O and then I map from X to O. And those are the things I expose, right? But then and then you might not expose like, yeah, Ponte-P, you know, like you might not expose everything. You might have some internal dynamics that is not exposed. So in this setup, we do a simpler thing, which is to say, well, every system is by default equipped with the full observation map, right? So I'm exposing all my internals. So you can, at any point, you can attach some wire to my state and just read it, okay? So that simplifies a bit the treatment. But since every system can be like quotiented down to an observable system, that's not a big, too big of an assumption. So these are notion of systems, all right? And let me also point out that, so this is part of like a more general class of systems that's like dealt with in this work on categorical systems theory that we do. And what we do in this paper can be generalized to that wider class of systems that covers, for example, ODEs, covers non-deterministic monoautomata, other like things you could think of. So let's say this is like a toy model of a larger situation. And then as a category theorist, I'm legally obliged to tell you what the maps of systems are. And this is actually like a big part of this approach to the internal model principle. So what is a map of systems? Is a way to compare two systems to say that a system X relates to some other system X prime. Notice that X and X prime can have in principle different interfaces. Okay. And so in order to relate X and X prime, we need both a map on states, right? That tells me how the states of X corresponds to states of X prime, and a map on inputs or the interface, right? So, and this map of inputs is not just a map from I to I prime, but depends on X, right? And that's a very important feature of this, like of this way of characterizing systems. And what can I say? It's formally correct from a very mathematically motivated point of view. From a less of a mathematical point of view, why would you do this? And the idea is that you should think of I as really like some change that any state of X can go through at any point, right? So here we're looking at a particular case in which this changes. So the things that can happen to a state are always the same throughout the dynamics, right? no matter the state I'm in, I'm always going to receive an I and act based on that. But in fact, this is not a given. Like you could have different observations coming to you, like different types of observations at different point of the dynamics, right? And that's actually a really important feature to describe behavioral systems like in a really, really well behaved way.
Do you have an example of that?
An example of this.
Naively, I would say, okay, to relate two systems to each other, you sort of relate their states to each other, and then since they're both open, you have to sort of relate their wires to each other.
Yeah.
But there's something more. You just don't just relate their wires, the interfaces to each other.
Yeah. So I'll show you an example later related to the setup of this, which I think describes pretty well why it is a good idea. Okay, so you have these two maps and you want these to be compatible with the dynamics, right? So you map the states, you map the inputs, and then you want this to commute with the dynamics, all right? Which simply means that this equation is obeyed for every x, every I, right? Are we good on this? And then using this notion of map, oh, well, I have to tell you, if I have two consecutive maps, how do I compose them? Again, as a category theorist, I would like to do this. So if you have f going from x to x prime and g from x prime to x second, then the composite as just like on states is given by the composite of the maps on states, really easy. And then on interfaces, on inputs, you have this slightly more complicated expression, which is just doing this, right? So I push forward x using f of s, I use f of I to get I prime, and then I have an x prime and an I prime, gi, and I do the composite, okay?
Should this also be from a pair of two functions? I mean, you're going from if a function going from. Oh no, yeah.
And then using this notion of maps, I can tell you what a subsystem is. What is a subsystem? Is basically given by a map of systems from x prime to x, which is an inclusion on states, right? So I'm looking at a subset of x. And since this is a map of systems, this means that this inclusion commutes with the dynamics. So evolving inside x prime doesn't is the same as evolving with respect to x. And since x prime is a system by itself, this means also that evolution is closed, right? So I'm gonna stay in x prime as I move. And also our notion of subsystem is the identity on input. So we think of x prime as receiving the same inputs as x, okay? So this is x prime ends up just being a forward invariant subset of x, all right? Which means that for every, if I'm in x prime and I receive any input whatsoever, I'm gonna evolve to a new state, which is still in x prime, all right?
So x prime is the smaller system.
It's a smaller system, yeah.
Right, it's the subsystem.
Yeah. And then a further refinement of this notion is that of attracting subsystem, right? So an attractive subsystem is a subsystem, we call x star here, that moreover is like, yeah, eventually all the states in x are going to end in x star, right? This means that if you give me a state in x, there's going to be an n natural number such that for all times after n and all inputs, x is going to be in x prime when I evolve it n time steps. Did that make sense? Yeah.
So let's say you have a machine that that has like two loops that are disconnected. So you would say there are two subsystems because it's two loops?
Yeah.
But it's not like a factorization, it's not a for training, it's a different sort of part interface space.
Yeah.
Is that a weird definition of a subsystem?
Maybe, yeah.
Because it's not a system, it's a set of states.
Yeah. Or you could say sort of a subclass of behavior. not like a prediction of the.
Yeah, I mean, there's two schools of definitions of subsystem. One is indeed what you propose, right? You should like quotient and say, well, I'm ignoring some things, some variables, some observations, and that ignoring defines a subsystem, right? So that's like a quotient. And then the other school that says, no, well, a subsystem should be really like a subdynamics of the system. So I look at a piece of the dynamics that is like living on its own. So that's the definition we take.
Would it be fair to say that the subsystem in this definition is a subset of states that is closed under the update function?
Yeah, precisely. Precisely. All right. And then now we start looking at the setup for the theorem. I'm awkwardly on the.
You can turn off your camera, then you'll disappear.
I can turn off my camera. No.
Nice.
What should I do?
You can stop the overlay, no?
No, I should be.
How did you start
Well,
it?
I'll do this.
Ah,
All right. But now I can turn off my camera so you can see me. All right, so this is the setup of the internal model principle we are going to talk about today. So what I mean by the setup, so this is like the first assumption is that this is the kind of system we're going to talk about. So it's a system made of three components, C being the controller, P being the plant, E being the environment or external world.
and you say plant, and you mean like that derives from like a factory plant? Or something?
Yeah,
Or-
precisely. It's like control theoretic plant.
Not that one.
But if you're in green, if C is a gardener, P would really be a physical actual plant. All right. And you see like these arrows encode like where the observations from a system like end up influencing another system. So we see that the controller, let's say the plant is observing the controller and receiving inputs from it. So we get that C going there. And conversely, C is observing the plant and receiving inputs from it. So C is looking at the state of the plant, and plant is influenced by the state of the controller. Whereas the environment is autonomous, meaning that it doesn't observe any other system, but it's influencing P. So P is receiving a control signal from the controller, but also a disturbance from the environment.
The controller has no influence on the environment.
No. So this is a very important point, actually. Like if you add an observation on the other side, this whole thing crumbles, which is an interesting fact. And
Even an observation from E to C would break it.
well, I didn't think about that. So my to fit, I don't know. But like that's not super natural thing to do. Well, okay, no, it wouldn't crumble because you can always observe E through P,
Oh, sure.
right?
Yeah.
So ideally, you could come up with something like this. But then if you observe the environment, then that's a problem because at some point, we're going to use that E is an autonomous system, meaning the update doesn't use anything else, right? But maybe not. Okay, maybe I'm saying maybe that's not true. Okay, we'll see later and then come back to this point. Because at some point we change the setup and maybe that actually works.
This question?
Yeah.
It's important that the environment do not affect the control.
The environment does not affect the controller. No, as I said, actually, like it does affect the controller through P. So ideally P could just be relaying what's happening to it, right? So that's not a crucial thing. So just let me draw attention to so S is the full system. So first of all, okay, let me draw attention to this thing. As you see, like each system is exposing its state, right? So like this is an open system in the sense that we could ideally have other bits Oh God, I'm touching it. That could be other bits of systems like reading C, reading P, reading E, right? And we don't care about that. Okay. So we're just looking at this bit of the world. And the composite, we call it S, and it has an update function that so it's an autonomous evolution, right? Because it doesn't use any other inputs from the external world. So we're closed in that sense, but open in the sense that we still expose our variables. And you can see like the update of E doesn't involve any other, doesn't involve P and C. Yeah, the update of P involves everything, and the update of C involves everything except E, right? And is directly corresponding to the way we constructed this system, okay? So the first assumption is, this is the system we're going to talk about. Oh, and here we come to your question, like, what does that definition of map buy us? It buys us this this kind of maps. So let me talk especially about pi c, which is actually the only one we'll use later. So pi c is a map of systems from the full system to the controller, which is given by on states, is given by projecting out the states of S to the states of C, right? So the states of S are E times P times C, and we can throw away E, throw away P, and define and get C. So this witnesses C as a subsystem in the sense of Fernando, right? So it's like a piece of the larger system where we ignore some other aspects. And we see that, okay, we can define that on states, but what about interfaces? So the inputs of the full system are trivial, is autonomous. So in order to map to C, we couldn't just give a map between the inputs of S, which are trivial, 1, and the inputs of C, which is P, right? Something of the plant. So that's where having like this extra argument becomes very useful, right? Because now a map, like the map of interfaces that goes from, this is the thing we should be looking at, right? So it goes from S times 1 to P. And since there is S around, we can get a P by projecting the state of P out of S, right? So if we only had 1, maybe I hope people see from Zoom. So if we had this kind of map of inputs, we wouldn't know what to pick, right? Because I don't know which input, well, like which state of the plan I should pick. But if I have something of this form, then I can just project away P, right? The full state of the system is the state of like a state of E, a state of P, and a state of C. And then I can just pick the state of P, right?
And you want this map because
well, I want it because later I'm gonna use it. But also it kind of makes sense that I can project out the 3 components of the system, right? So that's the thing. Like, I think the best justifications I have for these kind of maps are, first, they're very useful in practice, and second, they're very mathematically natural to define, at least from where I come from.
they're basically just the projections.
Well, for these 3 maps in particular are natural because they're just projections, right? I was talking about like this shape of the map between inputs, right? Like it might look a bit unjustified, but like then in practice and like in theory, it's actually a well justified thing to look at. Right. So second part. So we have our system, now we need a regulation problem, right? So a regulation problem for the purposes of this talk is going to be a subset of the joint state space of environment and plant, right? So we have a set of states we deem good, which are states of the environment and states of the plant. And that's like the maximal general thing we can do with this setup, right? So
you have an opinion about the environment as well.
Yeah, you could not, right? You could say this is E times my wish for P, right? My goal for P. But you could also say, well, I like the environment to be in a certain state. Specifically, you could be like, if the environment is like nuclear apocalypse, then my hopes to regulate this are off, right? And so you can use that to sort of like give yourself a little like give yourself a break about like how much of the environment you want to actually account for, right?
But the controller can actually not affect the environment.
The controller cannot affect, no. That's why I say this is more of a wish. This is more saying like, what can I actually do about E, right? Right. There's like a set of disturbances that I can actually regulate.
Right.
So in this case, like picking out a subset of E means that, right? Or another way to see it is that this is actually, you could see this as some kind of dependent pair. So you can say your goal on P depends on E, right?
Exactly.
So you can say in this state of the environment, if like this is the state of the environment, then I want this subset of P, right?
If there's a high demand for my product, I want to be producing a lot.
Yeah.
If there's a low demand.
Right. So yeah, you might have a dependency on the states you like in P on the state of the environment, right? So this plays this double role of being both like a way to limit how much effective you can be, like you want to be, right? And both a way to actually specify the goal you want on P, right? So that's just like our specification, our goal. And then assumption is that C is a good regulator. Okay, that for us means that there exists a non-trivial attracting subsystem of S that we call S star, which is contained in, I didn't tell you what K is here. So K is C times K tilde, right? So K tilde is a subset of E times P. If I want a subset of the whole system, then I have to attach C, right? So in this setup, we don't have any dependency of the goal on C, right? So every state of the controller is fine. Not every state of the environment plant subsystem, right? So what we're saying here is C is a good regulator if there is a non-trivial subset of the goal that we can actually achieve and stay in, right? So that's an attitude, like it's not a universal notion of good regulator, okay? Like you might just say, I just want to reach this good state and then that's it, right? That's also a possible thing. Or you can say, I want to be here like infinitely often instead of always, right? This is saying I can reach the goal and once I reach it, I'm staying there, right? So it doesn't account for, oh no, I'm out of the goal now, I'm gonna come back, right? That's not something you can do with this setup.
Given the thing about the effects of the environment, could it be that there's multiple good regulation subsystems that you want to track depending on the environment?
Absolutely. So yeah,
does the regulation problem also become about which control to be in? The secondary
which state of the control?
You've got two subsystems. One is good in one environmental condition, another is good in another one. There's another regulation problem about how to switch between them.
Absolutely, yeah. So that's an interesting point. Like, there's two different things. There's like being an effective regulator, good regulator, and being like an optimal regulator in some sense, right? And the structure of regulators of a given, like solvers of a given regulation problem is non-trivial. And for example, you can do something like this. You can have controllers that are geared towards a specific like sub goal, and then you can put them together.
The solve just means that one is.
Yeah. And depending on what extra criteria you put on the regulation problem, then your notion of optimal regulator changes, right? But for this to go through, you just need this to be like a non-trivial regulator. And also we're gonna see that like there's like these two aspects are linked. Like the more trivial you are as a regulator, the more trivial this theorem becomes. The less trivial you are as a regulator, the less trivial the theorem becomes. Yeah.
The definition of attracting subsystem, does it depend on the initial condition of the system?
No.
Because it could be that there is one point isolated that you stay there forever, you start there, but you will never start there. all the rest of the points of that.
Yeah.
And still do,
So the definition we've given does not depend on that because there's no initial states. But again, you could add initial state. Like this is pretty stable framework.
then you could solve it in a trivial way that is actually not useful at all. Right?
Mm.
You could
How?
solve the regulation, C could solve the regulation problem in this one state that has zero probability. And that will never reach in practice, right?
I guess. But like, if it's a subset of K, then it is something you want to account for, right? Because if that state is something you don't want to account for, you can just not have it in K, right?
But there's no condition on the fact that the attracting subsystem is reachable. It simply exists.
Well, it's reachable by definition, right? Because every state of S eventually ends up in a star. So S star is reachable from everywhere, actually.
So for any initial condition, eventually you will end up.
Yeah.
Okay.
So it, like, if anything, this is a very strong setup, right? But it should be like really trivial to just like have systems with initial states instead of just systems and then do everything with that. And so now you have a weaker setting, right? And you can at least specify exactly where you started from. Right. So okay, so we are now gonna focus on this S star regime. Okay, so S star is the regime in which the control problem is like solved in a sense. So we are in the good state and we're staying in the good state and everybody's happy. So the first thing we do is realize the C star. So every time you see a star now, that means the restriction of that system, so in this case the controller, those states that are in the attracting subsystem, right? So I think 1M called this active states, right? That's the X plus we've seen at the beginning. So C star are those like active controller states that are actually engaged in the dynamics when we are in S star. And the whole system now looks like this, like starred. There's a whole subsystem. Each component is also participating here. And now,
Right. So a star is a subsystem because the star guarantees that it's closed on their updates.
yeah. So like a subdynamics, yeah. And note that we have a map pi C star, again, that like witnesses that C star is a component in S star, okay? So it's here participating in the larger structure of S star. And now let me tell you where we're going to go. So our notion of model, which is the following. So a model of X being a system is going to be given by two parts. Another system M, which we call the archetype, we can call like the model as in like the thing we use to model X. Mu, which is a map of systems from X to M, which instead the model per se. So it's the archetype. So it's like this archetypical dynamics that we want to use, the simplified dynamics. With also the data on how like the thing we're modeling is attached to this, right? And that's a very important thing, right? It's not enough to say there is a system M, because if you don't know how it relates to the thing that we actually want to model, right? And then we want two conditions on this map. The first is that the map on states of mu is surjective, and the second is that for every state X, the map mu I X is surjective, right? So we also say fiber-wise surjective in this case. And let me try to motivate why this is a good notion of model. So one good way to understand this is to read this map. So this is like a very classical maneuver in abstract mathematics. You represent a family of sets as a map, right? So we can, to a first approximation, understand mu as representing a family of sets of subset of X, right? So for each state of M, little m, there is a set of state, the per image of M in X, which is called the fiber over M. And you can think of those as all those elements, all those states of X that according to the model we decided to use are equally good, okay, are the same to some extent, right? So we isolated some variables, we coarse grained the states, and to say, well, this is when X is in this state, I'm going to say it's in state M, right? And then the important thing is that this mapping is compatible with the dynamics. So if you have a transition here, so let's say you have a state in M, right? M0, and there's some state in X0 that we know corresponds to M0 through the map mu. And then what we can do is sort of use M to reason about X. What does that mean? That we can say, okay, if I'm in M0 and I receive input J, so I do this experiment J, and I end up in M1, can I do this? Can I use this to track the behavior of X, right? So can I use the evolution of M to describe the evolution of X? And if mu is a model, so it's surjective on states and fiberwise on inputs, then we can do that. What does that mean? That for such a transition in M, there's always going to correspond a transition in X, possibly with a different input I, which is then projecting back to J, that's going to some new state X1, which we know is encoded by M1, right? So if I have a state in X that it's encoded by M0 and I evolve M0, then I get a new state in X, which is tracked by M1, okay? So I can use M to reason about the dynamics of X, right?
M seems very similar to a coarse graining.
Yeah.
Right? It's exactly a coarse graining.
It's exactly a coarse graining, yeah.
If you're changing states in the coarse grained version, you know that you at least change states.
Yeah, exactly. And a way to see this is to say the same thing I said now, is to say that there is is to do this thing. So now you can say, well, M has a dynamic, so this update map. Well, I forgot the inputs and outputs here. Okay, let's see we're in an autonomous case. Okay, so M is its own dynamics. And then we look at a fiber over M. So we look at all the states of X that are actually encoded by M. Then if we evolve all those states, we get a subset of the states that I would get if I were looking at the fiber of the evolution of M, right? So I push forward all the states in X that correspond to M0, and I get some new subset, and I know that this subset of X is going to be encoded by whatever, by M1, right? So I'm going through this transition. Here I have a bunch of states, I evolve them, and I get a bunch of states. They might be less than the states encoded by M1, because like if I just know M1, I know something about X. But if I know that I came to M1 through M0 with transition J, I know more. So I know that the states encoded by that are just the ones that are compatible with that transition. So this means that we have this square which commutes up to inclusion, right? And so a way to see this, that it's like the topic of the second part of the paper is, well, this map is encoding sort of belief about X with the states of M, right? And these beliefs are not just like a family of distributions, or in this case, a family of subsets, but they are compatible with the dynamics, right? So it's a dynamical belief, right?
So it commutes up to inclusion because if you take the path that updates X, then the set you end up with is included in the other path, right?
Yeah.
It's that direction. The inclusion is that direction.
Because like this is saying, well, if you look at a state over some M0, right, and you evolve it, then this must be over the evolution of M0. But in principle, there could be more things, right? So it's at least those things.
So I had it the wrong way around.
Oh, wait, Sorry, that goes the wrong way.
Okay, right.
Sorry, guys. It should point the other direction. Should point this, right? So the upper path is included in the lower path.
Okay, then I get it.
All right. That's what happens when you prepare slides.
Yeah.
Well, too late. All right, and let me also say something about like what is a trivial model. So it can very well happen that you have like a system X, which is just given by your model times some other system, and these two parts of the systems like evolve completely independently, so that the beliefs encoded by M are completely useless, right? Because M is encoding some subset of X, namely everything in F. So here I assume that X is equal to M times F, right? And then to any state of M, there corresponds like the entirety of F, right? And this would not be a problem if also the dynamics didn't decompose, right? If the dynamic decomposes like this, then knowing something about M doesn't tell me anything about F because F is completely independent from M, right? So this is a notion of trivial model. As a known example, this is maybe a bit weird. So one thing that looks like a trivial model but is not is the map pi e that projects the system state to the environment state, right? So why does this look like a trivial model? Because any state of the environment has a fiber, which is the entirety of all the states of the controllers and the states of the plan. So this looks like a trivial model in that sense. Why isn't it trivial? Because if I know that I'm in E0, so if I know the state of the environment, I can constrain the dynamics on the controller and the plan, right? So this is not a trivial model. It would be a trivial model if the environment were fully disconnected from the rest of the system, in which case knowing the state of the environment does not afford you any knowledge about the rest of the system, right? So this is to drive home a point, which is it's really important to both look at the maps, as in like the set theoretical maps between states, but also at what they do to the dynamics, right? So these are not sets; these are dynamical systems. Therefore, like these notions are less trivial than might look at first sight. All right, let me conclude. So we have something that looks like a model in our setup so far, which is the map pi star, which is like encoding states of the system, a star, in states of the controller, right? So we can use a state of the controller to like encode a belief about where the plant and the environment are. The problem with this map is that we cannot in general like use it as a dynamical model, because if I'm in state C0 and I evolve with it's like I read something from the plant, then there's in general no way to use to find a transition in the system above that also ends up in C1. Why is it the case? Because transition here would be using the information that I'm in C0, and then would pick up state of the plant and a state of the environment, and then it would evolve those. But then the state of environment that I picked here doesn't need to be the state of environment I picked here, right? So what happens if I naively evolve? I end up somewhere else, which is not necessarily over C1, right? So in this case, the state of the controller is not tracking the state of the whole system, right?
Sorry.
Yeah.
How do you work with beliefs in this setup?
What do you mean?
You mentioned that there were some beliefs about how the states were actually.
Well, so you can think of like this map, right, as a kind of Markov kernel, right? So a state in M encodes a distribution, in this case is a possibilistic distribution, over the states of X. You can think of those as a state, as a belief that you are encoding in M, right? All right, so naively this doesn't work, and that's where the third assumption of this setup comes in, which is it's called the error feedback structure, and that's been there, as we see, since the beginning of the good regulator theorem literature, which is that actually when we are in this star dynamics, so we are in the happy regime, then actually C star doesn't need to read the planned state, right? So the way you should picture this is that if the plant is happy, what I'm reading from the plant is not gonna affect the controller, because the controller just needs to make the plant happy. If the plant is already happy, the controller doesn't need to do anything, right? So the controller is gonna have its internal dynamics, but it's not gonna receive any, it's not gonna get any information from the plant. Why?
It will only stay happy as long as the controller
Yeah.
intervenes like that.
So this is all like a case in which like we put ourselves in a situation in which something trivializes because we are in that situation, right? So in general, this is not true, of course. But if you look at those cases in which like you postulate that the plant is happy, then you know that the controller will not need to do anything.
Okay.
Specifically, like the state of the plant, any happy state of the plant is not gonna influence the controller, right? So think about it this way: if a thermostat is measuring like the target temperature, if we assume that it's measuring the target temperature because we are in the good state where the target temperature has been reached, then it's as if the controller is not reading the target temperature, right? Because at the target temperature, the controller is not like intervening, right?
So, but being in that state is stronger than just putting the star there. Because that's not true for all.
So, no. When we are in a star state, then we are inside K, and then we are happy. So the extra assumption here is not that we are in star; it's that there's no, actually that C is autonomous. So C star is independent from P star at this point. So in this regime, by assumption, C star is not actually using the data from the plan, because in this regime, it already knows that the plan is happy, right?
It's only true for a short period of time, potentially.
Well, so in this setup, it's going to be true forever, because once we are in C star, once we are in S star, once we are in the good regime, then we guarantee we're always there, right?
But once your thermostat realizes, okay, we're at temperature, you cannot cut the wire that leads to the actual heating element, because...
No, in fact, C star is still intervening on P, but it's not reading from P star, right?
Okay.
Yeah, maybe a phrase that a bit confusingly. Yeah.
Okay.
Go from closed loop to open loop.
Sure. So
yeah, exactly.
It does still get to it.
Yeah. Good. So let me say this is not like a universal assumption, of course. Like it very well might be the case that you still need to read exactly how P star is happy, so you can continue to keep it happy, right? So that's why it's called error feedback structure, because this is true specifically for those cases in classical control theory in which like you have this kind of signal that comes from P star. That's sort of a reference, right? That's a difference from like a happy signal, and then you use that reference, that delta to drive the dynamics of C star. Like that delta is 0 because we're in P star, then there's nothing to drive C, right? So this is just saying that if you add 0 to the to like this thermostat thingy, then it's like not doing anything, right? All right.
At some point, there is a strong assumption that once you are good, then you're good forever.
Yeah.
Not like the shower where you put the shower nice and then sometimes again burning and you have to turn it down because the effect is low.
Also for E star, right? The assumption is that that's a closed. Because the conditions of E star, right, will affect P star, but you've assumed that that's also closed.
Yeah.
And non-interacting, right? So if you have two subsystems of E, which are good, and they're connected in some way, this will break.
Yeah. So we assume that there is a subregime in which the regulation can be effective and stay effective, right? So even if you deviate, you're still somewhere it can bring you back, right?
Yeah, okay, E can change a lot. But we know that we're in that
within its
regime
good
of
regime,
G
yeah.
star, we can actually always correct
Yeah,
for that.
yeah. But you can correct open loop, that's a strong assumption.
You have to be able to read it, right? Correct for it, then you need
Right.
that error back. That's a stronger assumption.
Yeah, exactly.
Yeah. But now with this assumption, we can prove our theorem. Yay. So how do we prove the theorem? Well, we solved the problem we had before, because now there is no, like, the evolution of C doesn't depend on P, right? So whatever P we choose here, we know we're gonna end up over a state of C that is compatible, right? Because where we end up in C does not depend on the state of the plan. So we always end up in the same C1 star. All right. So with this third assumption, the arrow feedback structure, we can prove basically, at this point, the proof is completely trivial, that this map is a model because it's surjective, because it's a projection, it's surjective on inputs because these are both autonomous, right? Being autonomous systems, it's surjective on input because they have the same inputs. And so you can see as a model, this is encoding the controller is encoding the beliefs about a star in this way, right? So if I'm in the active controller, in the attracting controller, then each of my states is just believing that P and E are in the good state as well, right? And then the extra non-trivial bit is how this evolves, right? So I know how this evolves because I know which state of the controller I am, and then I can use that to know where the system will go because I decide where the system goes, right? Up to knowing where E and P are with some precision.
So is the analogy here that thermostat, once it's reached the right temperature, it can sort of know, okay, and I know the room I'm in, so that I know that whenever I've reached the temperature, every 10 minutes, I turn the heater on for 2 seconds to keep this temperature.
Yeah.
And I don't even need to read anything.
I think that's a great metaphor. Well, example. Yeah. It's like we accounted for enough of the world to be able to say this. Again, there's a very strong assumption. I'm not gonna pretend this is like, yay. But the hope is that like we can start from here and then improve on this, right? And once we understand where each assumption comes in.
Where the model comes in, right?
So this is the model, right? So where we think of C star as modeling a star, right?
The model is the fact that you can forget about you can go open loop.
Now the model is the fact that we have this map, right? So if you like, it's what Abel said. Like in this situation, then it means that the controller somehow knows how the system, the plant and environment are going to behave, right? Just like with enough accuracy to be able to be in the successful state, right?
The cost training is the fact that you forget about can not observe anything.
Yeah.
Because you can predict well enough.
You don't, yeah.
But what's kind of weird is that, so I always interpreted this good regulator, this model that you would have to have as a good regulator, be something that you're sort of actively working with. But once you're in this setting, now you could, like, the new controller that gets hired for the job, you can just tell him, we're in the area where you don't need to worry about the whole complicated factory, just every 10 minutes press this button. And that new controller has no model of the world. It's just told to press the button every 5 minutes so that it stays warm.
But that is a model in the sense that you have to control the thing that you control.
Yeah, so here,
If that's the definition model, then the good regulator theory triggered.
If you had 2 rooms, one where you have an outer room with a thermostat, which was turned off and on, and controlled the temperature perfectly, that's your environment. You then had another room, which could have a model of that room, right? So then that thermostat would just copy this, and it wouldn't need to measure anymore, it's just copying the same cycle.
Right.
This is kind of
And then you can have equivalent classes of rooms that are the ones that require the same amount of intermix.
Sure. Yeah.
so Nathaniel Virgo loves to say that this is actually the external model principle. Because if you think about it, what's happening here is that we're not proving that C star is somehow made of a model and a dynamics that's querying the model and updating the model, right? What we're saying is that somehow, like, whomever designed this thing knew what was going on, right?
Right.
And specifically, like us, from an external point of view, can use C star to model S star, right?
Okay.
But this map is external from the systems, right? This is something that it's not part of the systems themselves. It's something that, from an external point of view, we can use to compare to the systems, right? So from that point of view, we can use C star. Well, we can use pi star to model S star using C star. But internally, there's no guarantee that that's actually what's going on, right? It means that at some point when we designed the systems, then we knew what was going on, right? We knew what was going on well enough that we can, like, indeed do this thing.
Okay, so using the thermostat analogy again, the
Yeah.
normal one is boring because S star is a single point, namely a single temperature, or P star is a single element.
Right.
But somehow you're saying, okay, now it's interesting if you want it to be colder at night in your room, then just by observing how often the controller is pressing the button, you can understand if it's day or night. And in that sense, the controller becomes
Yeah.
a model
Yeah.
for the reality. You can see how it's controlling, and that says exactly what you're interested in. And
Yeah.
is it day or night? Right, I get it. Thank you.
Very well put. All right. So just for completeness, what do Wanham and Hepburn prove? They prove this extra thing. And I think here there's a slight misunderstanding on what, like, a model is, which I think it's really beautiful. So there is they assume this fourth thing, which is that, well, actually, E star completely determines S star. Oh, did I get disconnected?
Is it continuing on your screen?
It's like,
Oh,
oh,
that's weird. Did your internet drop out somehow?
no, I think it's just Eduron being Eduron.
It seems connected. Shall I give you a hotspot? See if that works.
Really, we're regulating this system. I mean.
No, exactly.
That's okay. Okay, it's back.
Oh, you're back. Good.
Okay, we're back. So, Wanham and Hepburn, they had this extra assumption, where they assume that E star, so like the states of the environment in which we are capable of doing regulation, is isomorphic to S star, which simply means that each environment state has a unique like triple of a controller state and a plant state, and that environment state associated to it, right? So there's exactly one way to regulate that state of the environment, and exactly one way that the plant could be in at that point, which is a fairly strong assumption. So what I think they do here, they were like, oh, I want C to model E. Like, the things they had in mind is, I want the controller to have a model of the environment, right? Because a model of the plant, well, that's already in the design of the controller. That's not interesting. But actually what they end up doing here is completely trivialize the situation, at least trivialize it to some extent, and they completely like they don't account for C anymore, right? So in pi C star, specifically in S star, like, we have the plant and the environment, and that feels like the good thing to be modeling, right? If I'm a controller, I need to know what's happening to the plant and what's happening to the environment, at least. But one might be like, oh, well, it also has C star in it. Like S star is also has the dynamics of C star. And so that looks a bit like redundant or even like I don't know, circular. It's not, because of the way that a model is interpreted from like this point of view that is actually representing a family of subsets which are compatible with the dynamics. So when you have a family of subsets, like each fiber is not like does not know anything about what's below it, right? Because let's go back here. So a fiber over C0 star is indeed like some states of the plant and the new environment, right? So there's no C there. Like what the thing that C is encoding is the rest. But when you add everything together, of course, like to keep track of exactly where each of these things should go in C star, then you need to have also that bit around, right? That is to say, you're always going to find the dynamic of the model in the things you're modeling, right? Because by definition, basically, because you have to. So there's no need to actually exclude that the way they do it to have, I think, like a decent notion of the theorem, right? So there's actually a assumption that we can happily drop, in my opinion, because we still get a theorem that says C star is modeling the plant in the environment, right? There's no need to like throw away the plant somehow and the controller. And that's it. Thank you. Questions,
Any questions?
critiques, or facts?
How luxurious is it for the environment not to care about what's happening in the plant? I mean, your thermostat in your room and the world, sure, but a big factory and the area around it and everything that's going on might be different, right? I mean, you're using water from a river to, I don't know, do stuff, and then that river disappears. So now all your things actually affect the environment quite a lot.
It's a definitely a non-trivial assumption, yeah. But I think we can actually do away with it here, because here you see that the only thing you need here is to be able to, like, you need C star to be autonomous, basically. But here, this evolution, specifically the evolution of E, could easily depend on C and P, right? So I think that's actually a thing we overlooked that we could generalize on, right?
And you can always, I think, expand your definition of plant or the thing you want to regulate. Because at some point you're going to say, okay, the other side of the world probably doesn't affect my factory somewhere.
And in the short term, but then again,
Yeah.
you just do a separate.
Yeah. There's also this point which, like, E here is really something you'd like not to talk about, in my opinion. Like, because what you really like to say is that I am an open system, and like C and P form an open system, and my goal is to regulate P in some conditions, right? But then I don't need to know like what the rest of the universe is doing, right? I just need to know in which way the rest of the universe can condition my plan, right?
Yeah, actually,
That's the only thing you need to know.
We were asking the question before, how could the controller access E? We said through P, but it's open, so E can just be looped back to C. Oh no, it's only open to the outside.
Yeah,
It exposes something.
it's only exposed.
It only exposes.
Yeah.
Okay.
Something like this.
No,
Yeah.
that's
So, but you raise a good point that actually there might be effects on the environment that you want to avoid, right? So you want,
Because it could push you out of the start, out of the happy state.
yeah. But
Then people start protesting.
but
Then all of a sudden you have to shut the thing down. You're not very happy.
yeah, but maybe then the point is that you should bring that part of the environment in your plant, right? Part of the thing you want to regulate, and not like the disturbances, because that's something you actually want to account for. Yeah.
What if there are, going back to this, multiple kind of subsystems? because this is a discrete system, so you've got some notion of timescale.
Mhm.
But what if one of these subsystems is massively longer in terms of its cyclic behavior?
Yeah, I don't know. What difference does it make?
Yeah, I don't know. So, yeah, just going back to this question about, the timescales of the plant affecting the environment, that's much, much slower than the control effects. Does this?
Is that the situation the world is in, right? Is the time effects are too slow for us to realize, so we assumed we're in this case, we're in a different case, and well, it affects how well we control what we're doing. For the purposes of controlling the plant, we don't care.
Then your set of, then your set of E still guarantees this, even if it's very, very long. It could be having it much slower timescales than your control loops. And this is, I guess, still the assumption.
Yeah, like at some point you have to decide which aspects of the environment you care about, right? And then, as you were saying, the aspects might not be completely accurate. Yeah.
My intuition for this assumption 3 is that you kind of switch from reacting to the environment to kind of predicting the environment. That kind of makes sense that you then use this assumption to kind of go to the fact that you also have a model for the environment. But I don't have that much for the other assumption that you need. What is there like an example that you have of a system where this assumption is broken, and you also maybe have some intuition that then your system is not modeling your environment?
So you mean examples in which the other two assumptions are broken?
Yeah, so I mean the assumption for the last assumption. Is there some intuition there that when this is broken, this assumption, that then kind of something goes wrong?
I mean, like any example in which the plant can be in many happy states with like respect to the same disturbance. I think that would be like if you have a thermostat governing a room, and the room has to stay like within a range of temperatures, right? And then like the state of the room, like there's many states of the room corresponding to like the same state of the environment in a sense, right? Which might be like the temperature outside. So I think it's not warranted to assume that there's only one possible state of the plant in that case, right? Yeah, but like now this to me seems more like a conceptual error than a like modeling error. I mean, it still constrains like the applicability of the theorem, but I think what they try to do is like fundamentally conceptually wrong. Like they want to exclude some things out of the model, whereas like being a model means exactly that you have those things, right? Yeah.
So I think my phrasing of the same question is
Hmm.
the 3 conditions that you're assuming seem to be sufficient, but are they necessary?
I think they're necessary, but not sufficient.
I mean, if you satisfy the 3 assumptions, then everything works.
No, okay, you're right. Yeah. And you're saying if I have this thing.
Like if you violate one of the 3, could you say there's
Oh.
no model at all?
If I violated one of the 3?
Then there is no model at all.
I don't have counterexamples in mind, but I can very clearly. I'm pretty confident, yes, like you can violate those and break it, like absolutely.
It's how you break it.
Like, well, it depends exactly how you formulate it then, I guess, right? Because like, for example, this hinges very heavily on the fact that you are in this like eventual regime, attracting regime. And so as long as you break like this one, the feedback structure, then it's very unlikely that you can just be talking about the same kind of model, right? You probably need to involve like the larger state and the larger controller. Same for like this. Yeah, like this one is pretty much that assumption, right? So if you change that, you need to change exactly what you mean, like exactly how the model is encoded, right, in this picture.
One related question, for me, the third assumption feels a bit strong.
Yeah.
But I was wondering, like, if you have a system that is in constant feedback and constantly adapting, so you cannot go to open loops. But then you sort of go meta and you say, well, there was a learning process. And now I learn how to do it. And although in practice, I need to be, adapting at this meta level, I don't need to learn anymore. So could you apply the theorem on that level and get around?
So you mean there's a transient in which I'm learning, and then you want to say that
You've already learned, so at the learning level, you can go. Although in the implementation of that learning, you need to continue because.
well, I think this is covered by this, right? Because you need to be error feedback only in the attracting regime, right?
Yeah, so my question is, would that trick solve the problem of failing to base assumption to be too strong?
I mean, I guess, but I can still think of cases in which you cannot really learn anything. Well, I mean, you can learn, and then that's not enough to always be like able to predict the disturbances, right? Like, say you're an inverted pendulum regulator, then there's nothing you can do to like say like predict the kicks I'm gonna throw at you, right? So the best you can say is like you might enlarge your happy states. Like as a designer, you might say it's enough for me to be not necessarily vertical, but to be somewhere I can go back to vertical, right? So that's how I read like the feasibility of these assumptions. Like you just need to account for that kind of disturbance, and then once you're in the regime you accounted for, then as someone was saying, you're basically in the predictive regime, and then that's something you can handle. But because you expanded what you consider like good, right? Good means regulating in a sense, regulatable.
So what's funny to me is that the model is somehow defined as a property of something that happens inside S star. But it's really the thing that gets you to S star.
No,
what you need the model for is to get to S star or P star. But it only appeared really once we were inside S star, right?
Well, yeah, this theorem is like, if you can do a successful regulation, then it means you have a model. And this is how you have a model,
yes,
right?
It sort of says that you must have had a model.
Yeah, right.
Yeah.
So what you say is true.
Yeah. Exactly. It's not a constructive proof of the model.
Yeah.
Showing that one must exist.
And then, yeah, again, it's showing that if you're doing this kind of regulation with the error feedback, then it must be is because you have this predictive model, right? So it's sort of saying that it doesn't mean that when you're outside that regime, you don't necessarily have a model, right? It just means that in that case, you still need to like know a lot about what's happening outside you. But with these assumptions, once you're in this regime, then you can basically just query your model.
If there is no model, then pi c star does not exist.
If there isn't a model,
if there was not this model, then there is no map pi c star that does this. Is that the right way to say it?
I guess. Yeah. I mean, in this setup, yes. Then
Any more questions? Otherwise, we thank Matteo again.